So as we all know, symmetry is an attribute of geometry shape, geometric shape in which, a shape is mapped onto itself by a rigid transformation. What do we call rigid transformation? We have, in our previous unit, I think last semester we talked about different kind of, no, I think unit 6, yes, we talked about different type of transformation, and we said we have two, the rigid one and the non-rigid one. The rigid one does not, the rigid transformation do not really change the shape or of our object. Okay, the pre-image and the image, the shape and the size are not altered, they are kept. But the non-rigid one will always change the shape. And the example of non-rigid one we work on later was dilation, but the rigid one we had rotation, translation, and reflection. So today we're going to talk squarely about symmetry, and then we're going to see how the kind of symmetry we have and then how they affect a polygon. So the first, the introductory part will be symmetry is an attribute of geometric shape in which a shape is mapped onto itself by a rigid transformation. And we have two types of symmetry. We have the reflectional symmetry and the rotational symmetry. The reflectional is always about a straight line. It might be horizontal, it might be vertical, okay? And the rotational one is always about a point, and it will move from 0 to 360 degrees. So let's quickly talk about the reflectional one. A figure has reflectional symmetry if, sorry, this is if. So if there's a line across which the figure can be reflected and mapped onto itself. What do we mean here? Like in this case here, as you can see this figure, this straight line here divide this out into two equal sides. So that by the time you fold, if you decide to just put this side onto the other side, it's just gonna merge on it without any side being longer or smaller, okay? It's gonna be just equal. And this, so this is a vertical reflectional symmetry. On the other side, we have two. We have the vertical one, which is this going downward. So it means if you take this triangle, you move it downward, it's just gonna close the other one downward there. Or another thing is that if you decide to use the horizontal one, if you fold this guy downward, it's gonna just take it like that. This one can just come downward to close the one, the triangle below, and be on top of it without one being bigger than the other. The other way around is if you decide to have this straight line. So this side here and this side, if you fold them towards the left right hand side, this guy gonna come here, and this guy gonna come and sit here. You're gonna see it when I try it on Agile Mind very soon. And the heart is not a polygon because no, it doesn't have straight side, okay? Because if we say a polygon is a plane figure, a plane figure with at least three straight lines, okay? So here, this here is a polygon because the side can be adjusted and put together. We have two triangles there, so it's six-sided. And this letter E2 is a polygon, even though it's not straight, but you can count the number of sides: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a dodecagon, but it's not regular because the sides are not all equal. So that's not what I really need today. What I need is just this straight line, this horizontal line, cutting it into two equal sides. Meaning, if I decide to take this part, the upper level downward, it's gonna come straight here and gonna close it up without one side being bigger than the other, okay? And then what we can say that it's possible for a shape to not have any line of symmetry. Yes, it's possible. We have different shapes like that where there's no line of symmetry. Like if I decide to draw something of this nature, I cannot create a line of symmetry here because if I put a straight line here, if I fold this side, it's gonna be something because since this side is already round, so if I fold it here, it might not cover this. And then if I decide to put a straight line here, this way, it means if this side now, if I fold this green side, see the way it's gonna be. This guy enters here, so it means this guy gonna enter this way. So you see, so the excess is here and the excess is here just not gonna make it, the right line, a line of symmetry. So it's possible for a shape to not have any line of symmetry. So line of symmetry is about when you have a straight line and then when you decide to fold the image the object you have, they will sit on top each other without any excess on any hole being seen. And we're gonna talk about the rotational symmetry. A figure, has rotational symmetry if there's a point that the figure can be rotated about can be rotated about between 0 and 360 degrees and map onto itself. It's like you have an object. If I decide to have this straight line this way and then I put a point here, this point is a point of symmetry. It's possible for me to have this same straight line coming towards this side. So this is going to be 180-degree rotation because if I turn this, if I twist this, okay, if this is 1, this is 2, 1 might come here and 2 might come up, okay? That's I'm twisting something like this, like your key. Yeah, if you insert your key into the keyhole in your door, once you turn it, if the side where we have those zigzag, they cut. Once you turn, the cut might go up, and the side that is smooth, straight, that form a straight line might just come downward. So those are just rotational symmetry where your key turns at certain angle so that you're able to close and open your door. And at that point here, so this point we're talking about is called the center of rotation, okay? We're gonna see all these things on Agile Mind through some demonstration. So do not be scared or do not be confused right now. So as you can see, letter H here, this left hand side here, this side, if I decide to, if this is to be 1, maybe 2, if I decide to turn it around, this one guy here might come down here and this 2 guy might come up here. And it's still gonna give the same shape. So this rotation is about 180-degree, at the center of rotation, okay? This symmetry is about 180-degree. And also if you have an equilateral triangle, it's also possible, to have a kind of rotation there, okay, at the point. Because if you have a point here, if this is 1, 2, 3, I'm gonna change color. If you turn this thing around, number 1 might come here, 2 will come at 3, and 3 will take the position of 1, and it goes on like that. The circle continues like that, okay? And also this figure beside here is what we call regular hexagon. As you can see too, it also undergoes a rotation about a symmetry, a rotational symmetry. If this is the center of rotation, okay, it means if this is 1, 2, 3, 4, 5, 6, there's possibility for 1 to come to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 1. And the circle continues like that. And again, you can perform the same rotation again. 6 comes to 2, 2, 2 comes to, the green one is now the one moving, okay? 6, green is 1 here, it comes to 2 here, so 1 here, 2 then comes to 3, 3 comes to 4, 4 comes to 5, 5 comes to 6. So you see, at 1, 1 became 5 when the rotation was performed. 100 rotation is performed, 5 became, 1 became 5, and it goes on like that. So if you continue the circle, here you might have 5, 6, 1, 2, 3, and then 4. You continue the circle again. 4 was here at position of 1. 4 will come here. 5 comes here. 6 comes here. 1. The yellow one comes here to be 2. The yellow one comes here to be 3. And the yellow one comes here to be this 2. And the yellow one comes here to be 3. And it goes on like that until 6, or 1 comes to its initial position, okay? So we're gonna quickly go on Agile Mind and see these things right now we're talking about. So what we know is that every shape has 360 symmetry. No matter what, if you have this particular shape here, if there's a point of rotational symmetry, this shape can go around itself towards 360, okay? If you have a point here, that point 1 will move until it comes back to point 1. That is like this isosceles triangle, this hexagon. 1 will move, 1 move to 2, it move, to 3, it move to 4, it's gonna move until it comes back to itself. So it's gonna, move 360 degrees to come to its initial position. That's why we say every shape has 360 symmetry. So when a shape only has this symmetry, we say that it does not have rotational symmetry. So we're gonna see why the statement says that. I'm gonna quickly go on Agile Mind, Agile Mind. Okay, who got here? So on our paper I gave everybody, if you go on Agile Mind, just go on topic 2 and then click on symmetry in polygons. This is symmetry in polygon, and then go to page 5. This is page 1, so you click here, page 2, page 3, page 4, and then page 5. So here the thing says select a shape from the pull down menu to explore its line symmetry, okay? So I'm gonna click here. This is isosceles triangle. As you can see, this isosceles triangle, I'm gonna try to move this point around to see if we have since this blue line is a straight line, so we're gonna see if an isosceles triangle has a reflectional symmetry, okay? So if I move here, no symmetry, as you can see. If I move towards this vertex, no symmetry. But if I move here, you see, it shows that there's a line of symmetry. Look at it. There's a line of symmetry. So one side, so when you fold one side, it's immediately cover the other side without stress. What about if I move it around again? You see, none, none, none. So how many times did I have this? Twice, because the first time I moved my dots, these dots downward, I had a line of symmetry, and then I moved the same point to its initial position to have another line of symmetry. And we have the same straight line. Since we have the same straight line here, what I'm gonna say is that I'm gonna say we only have one, the shape only has one line of symmetry. So you see, the only line of symmetry in an isosceles triangle is the one that goes through, the smallest angle and then cross the two equal angle into equal sides. So I'm gonna go, so if we go to our notes, what's in the note again? That's why in our notes here, we're gonna just say 1. And then to show it, we're gonna have this straight line going downward. And what about equilateral triangle? Let me check equilateral triangle. The second option here now, we're able to solve isosceles triangle, which only has one line of symmetry. The second one, equilateral triangle, I'm gonna try to move this guy around the edges. You see, first line of symmetry, because when you take one side, you fold it onto the other one, it forms symmetry. I'm also gonna go towards the other edge, going to one vertex, passing through the midpoint of the other. So when you fold, you see again, there's a line of symmetry here. And lastly, if I go towards this side, I also have a line of symmetry. You see how the animation is beautiful? So here it means we have only 3 lines of symmetry. So we got it. So I'm gonna come here and write 3. The first one is this. The second one is this. And the last one is this. And all of them meet at a point in the center here, okay? And the other one is, I'm gonna click on this arrow. Let's see parallelogram. A parallelogram, it's a quadrilateral, which means 4-sided figure, which is also a polygon, where opposite sides are parallel and equal. As you can see, the line down here is the same as the one up, and the 2 sides are the same. So we're gonna see if there's any line of symmetry. You see, no symmetry here at the edges. Why? Because if it has a line of symmetry, it means if I fold this side, on the other side, let me change color. If I decide to fold this side, I might have something of this nature. So it doesn't work. So you're gonna see by the time I finish with that animation. So if I put it this way, something strange might happen, because if I fold this side, it might just be something of this nature. You're gonna also see the animation towards that. And then if I decide to move it here, that will be catastrophic, because this side here, folding gonna just be something of this nature. And then lastly, if I perform the same thing here again, it's gonna also be the same thing. So here there's no strategic symmetry at all. See, if you fold, see what will have happened. It will have exceeded it. It will have gone, above that. If you fold along the diagonal, see what will have happened. If you fold along the other diagonal, see what will have happened outside. So that's why a parallelogram does not have line of symmetry, okay? So we're gonna say a parallelogram does not have line of symmetry, so 0 line of symmetry. And then the other one is the isosceles trapezoid. The isosceles trapezoid is also a four-sided figure, but it's isosceles because the two sides, left and right, are of the same measure, and then up and down are parallel. Okay, so isosceles because the left and right are of the same size, they have the same measure, but up and down the end is trapezoid because up and down are parallel. Okay, so we're gonna see if there's any symmetry here. So if I put this one here, you see no symmetry. Here there's a line of symmetry because if you put a straight line in that place, you draw the other side, you fold it, you're gonna sit on the other one. Here, let's see if there's symmetry. No. What about here? No. No. And I return to my initial position. So we only have one. So an isosceles trapezoid has only one line of symmetry. So I'm going to write one here. And it's just this line that passes through, because this side is the same as this side, and this side up here is parallel to this. So it means this line gonna cut, the trapezoid into two equal sides. And lastly, the regular hexagon. Since it's regular, I think it's gonna have 6. You see, first one, if you go through the two vertices, if you fold the lower level onto the upper level, you see, and also if you go through these two vertices again, the diagonals, you're just gonna start with the diagonals first, the longest ones. If you fold, it's gonna work. Here again, if I try this, I'm trying to fold the lower level maybe to the upper level. Okay, lower level goes up, it sits on it. I have 3, but what about if I try the midpoint of the sides? So if I try the midpoint of the left and right side, see, if you decide to have this, it goes up and down, it forms it again. Let me try the midpoint of these two sides as well. Okay, you see the line of symmetry gonna be drawn, and then the symmetry gonna be shown to you. So it sits exactly on the other side. So I'm gonna try the midpoint of this one again here too. You see exactly. So here, as you can see, if you count these blue lines, this is 1. Okay, you don't have to count it twice. So this is 1, 2, 3, 4, 5. You don't have to count it twice, so you have to be very careful not to repeat numbers. So if you put 1 here, 2, 3, 4, 5, or 6. If you come here at 7, 7 is also this one. So you stop counting from here. So you have 6. So we're gonna put 6 here. So we're gonna go and write it down there as well. So here, this one has 6. The first one is when you go through the vertices, opposite vertices, and then the next one, and they all meet at one point in the middle. The next one just go through the midpoint of sides, and midpoint of sides. So here, as you can see, you have number 1, 2, 3, 4, 5, 6. So you can't put 7 here again because 7 is the same as 1. Or the best thing you could have just done is by putting them into different colors. Let me just represent this guy in red, this guy in green, this guy in yellow, or yellow, this guy in yellow, and then maybe this guy in black. Yes, you can. And this guy another color entirely. So as you can see, the 6 colors are represented here. And we're going to then verify the rotational symmetry. So we're done with this. Let's go to rotational symmetry. For the rotational symmetry, I'm going to click on isosceles triangle first. As you can see, this is the point of this is the center of rotation here in the middle. And then I'm going to move this guy. So if I decide to put this edge here, nothing happened to the triangle. If I take it down here again, nothing happened. If I take it here, the red one doesn't sit on the blue one. If I take it here, it doesn't sit until it comes back to its original position, okay? And since it has been said that in our last statement that every shape has 360, so my green dots went from its initial position to its and came back to the same position, so it moved 360 degrees. So since every shape has 360 degree symmetry, when a shape only has this symmetry, so it means if a shape turns 360 times without repeating itself, it means we don't have a rotational symmetry. So here, not gonna have anything. So there's no, this isosceles triangle does not have rotational symmetry. You see, it moved all through round until it got to itself, so 360, so it doesn't have rotational symmetry. The next one is equilateral triangle. I'm gonna move this. If I move it to this edge, you see, this is the first rotation. I move it to this edge, you're gonna count with me, second rotation. I move it to this edge, the third one. So since this guy moved 3 times, okay, I'm gonna say, how do there's a way of calculating. Oh, I did not write this answer here. This is none. And on the other side, you need to find the degree. Since a rotation is 360 and isosceles triangle moved 3 times, so you're gonna divide 360 by 3, and then the answer is 120. So here it means this guy, it performed only 120 degree rotation, okay? So if I check, so its first movement is 120 and its second movement gonna be what? And how do you find the other rotations? Sorry, okay, you see its first movement 120. What about its second rotations? That's why it says 120 equals 3-fold, meaning the rotation happened 3 times. The 3-fold means 3 times, okay? So how do you find the first rotation is 120? The second rotation, we need to find the angle value, and the last rotation, we need to find the angle value. So how do you find the angle values here? It's quite simple. Since 120 is the first one, you continue adding 120. 120 plus 120 gives you 240. So first rotation is 120. Second gonna be 240. And then you add 120 again, 063. And once you reach 360, this is the last rotation. Since 360 is a normal rotation, okay, of an object, you don't need it. So these are the 2 folds you needed. And then the last one is 360, okay? So if they say an equilateral triangle has how many rotations? 3 rotations, but what are the angle of rotation? 120, 240. The 360 is not needed. And then we're gonna continue with the other one. The parallelogram. I'm gonna move this edge here. Nothing happened. I'm gonna move this edge here. Wow, our first rotation, the red on green, the red on blue, nothing happened. And then I came back to my initial position. This is our second rotation, okay? So here the rotation happened 2 times. What do we do? Here I'm gonna say, since a rotation will happen, an object rotates around itself 360 and it happens 2 times, you're gonna divide 360 by 2. And then when you do that, when you do 360 divided by 2, it gives you 180. And then, so it means 180 is the angle of rotation. 180. So it's happened 2 times. So they're gonna write 180 equals to 2-fold, meaning twice, happened twice. So how do you find the other times, it happens? You're just gonna do 180. You're gonna add 180 to 180. Just repeat the same number. 180 plus 180 is 360. Since 360 is a normal rotation of an object around itself, so this number is not needed. So it means the list of rotation is 180 here, which is what we got here. And then we're gonna go to the other figure, the isosceles trapezoid. I'm gonna move this guy to this place, nothing happened. This place, nothing happened. The red does not sit on the blue. The red does not sit on the blue. And the red just sat on the blue once. So, when you move back to its original position, it only sit there. So here, as I move my green dots around until it came back to its initial position, nothing happened. There was no rotation, okay? There was no rotational symmetry. So we can say none. So none. So here we just say none. Nothing happened here. And then the last one is the regular hexagon. Let's quickly go to the regular hexagon. So I'm gonna move this guy here, nothing happened. Here, our first rotation happened. Here, our second, we count, still counting, 3, 4, red sits on blue. 5, red sitting on blue. And then 6, red sitting on blue. So it's at 6 times on hit. So you're gonna do 360. Since a total rotation is always 360, you divide by the number of times, which is 6. And when you divide 360 by 6, it gives you 60 degrees. So it means the rotation was performed, at an angle. The least that happened is 60 degrees. And how many times? 6 times. The first rotation is always 60, is here is 60 degree, and it happens 6 times. That's why the thing is counting 5 or 6. So how do you find the other rotations? The list here is 60 degrees. So how to find the other ones? It's quite simple. Just take the least one, which is 60. You add it to itself. 60 plus 60 is 120. So here, the first one is 60 degree. Second one is 120. And then you had 60 again, the same number. 60 plus 120, that's 180. So the third one gonna be 180. Then you had another 60 again to 180 until you reach 360. So 180 plus 60, that's 240. So it means the other number is 240. Then you also had 60 again. When you had 60 to this guy, that's be 300. So the other number is 300. And then if you add 60 again, as you can see, that becomes 360. And 360, since is the biggest number, you don't need it. So those are the rotations that are performed here today. When you have an hexagon, when you have a regular hexagon, the rotational symmetry are 60 degree, 120, 180, 240, 300. So that was what we needed to do today.